Hello, and welcome everybody to my talk on fine-grained complexity of coloring unit disks. These are unit disks, and we want to color them in a way that no two disks which intersect have the same color. So you see there might be many blue disks, but I hope they're not intersecting here. Any two blue disks are not intersecting. This is joint work with Chababiro, Edouard Bonnet, Daniel Marx, and Pavel Tedeschi. And yeah, we did this work mainly while almost all of us were at SZTAKI in Hungary, Institute for Computer Science and Control. Okay, so let me introduce you to my co-authors. I guess most of you will know Daniel Marx. This is Edouard Bonnet, who was at this workshop also 2 years ago. Pavel Tedeschi, he's now in Warsaw. Edouard is now in London, and he will go to Lyon to work with Stefan Thomaset. This is me, and this is Chababiro. He was in Budapest, so we invited him over to SZTAKI where we worked together, and yeah. We met him at this workshop called Order and Geometry in Poland, where Pavel and I attended September 2016. Okay, and here you can see big pictures of my co-authors again. Yeah, so what I want to tell you in this talk, I want to tell you briefly about the square root phenomenon, and then explain you how our results fit into this line of research, and then the majority or the main part of this talk will give you some proof ingredients. Unfortunately, I will be very vague here at many times, so these are really ingredients and very rough ideas, but yeah, there are kind of gaps where you really need to trust me. Okay, so let's start with the square root phenomenon. So there are many problems in not computational geometry, in theoretical computer science, which cannot be solved in faster than exponential time, more or less using the brute force algorithm, which is best possible under the exponential time hypothesis. But then if you look at the same problem or a corresponding problem, either on planar graphs or maybe in a plane setting or geometric setting, then often the same problem suddenly can be solved dramatically faster. And we also have corresponding lower bounds. So this is a huge improvement. So many people work on solving maybe, I don't know, independent set a little bit faster than 2 to the and just improving the base. But suddenly here in the planar setting, instead of just improving the base, we can get a root n in the exponent, making it sub-exponential. Yeah, and this is often based either on true width, which would be the simplest case, but then also on bidimensionality, meaning either your tree width is low, then okay, then you can do tree width, or if your tree width is large, then you find a large grid minor, and then you're done as well. So maybe you don't have a small tree width necessarily, but if you have a large tree width, you have a grid minor, which is very helpful. Then also what is one trick that one can use to achieve these solutions or these running times is using the tree width of the solution. So maybe looking at independent set for intersection graphs of disks. Okay, so you look at the solution, and then you do a separator. You do like the Voronoi diagram of the solution and guess a separator in there, which is possible. It wouldn't be possible to get a small separator for disk intersection graphs in general. But yeah, but for the Voronoi diagram of the solution, it would be. So just to give an example. Yeah, and often the corresponding lower bound construction are pretty tricky. because they have to work in geometric setting and they need to be pretty tight. Whereas often in that case here they're easy. Well, maybe not always, but yeah. Okay. But also note that not all geometric problems admit a square root phenomenon. A classic example that I worked on was the Earth gallery problem, which cannot be solved in sub-exponential time. Also not the parameterized version. So yeah, it's often interesting to see when the square root phenomenon appears, when it doesn't appear. Yeah, and so we wanted to study coloring because we thought that was one topic that was not exploited yet. And so the first thing that you can note is that there is a square root phenomenon if you have 3 colors. So there is a 2 to the root of n algorithm using separators. You know, the graph is sparse, so this is kind of almost folklore, I would say. But then if you have many colors, let's say n over 10, then suddenly that doesn't work anymore. And kind of using some standard reductions that we found in literature, we could also find corresponding relevance. So the question for us, what is happening in between? So if you have maybe not a linear number of colors, maybe square root of n colors, what does a curve look like? Does it look like this? Or does it look like this? And it turns out it looks like that. It's a straight line where, well, I didn't tell you how we parameterize this, but we do this in the most natural way. So let's say we have n to the alpha colors, then we get a algorithm upper and lower bound of 2 to the n to the 1 plus alpha divided by 2. So let's say alpha is 0, then that would mean we have a constant number of colors, and then that would be the square root phenomenon, that would 2 to the n 1 over 2, and if alpha is 1, then we would be in this case, right? 1 plus 1 divided by 2 is 1, so we would have exponential time. Yeah, so that is essentially our result, and it's interesting that here in this geometric setting we get a speed up, but only if a few colors are needed, and there's kind of a continuous continuity here. Depending on the number of colors. Okay, so let's state the result formally and more precisely. So let's say alpha is fixed and n is the number of disks, and the number of colors is n to the alpha. Then it can be solved in 2 to the O of n to the 1 plus alpha divided by 2 times log n. So this log n factor I didn't tell you about. And it cannot be solved in the same without the log n factor, unless the exponential time hypothesis fails. Yeah, so this is our main theorem. And yeah, so in the remainder, I want to first tell you about this upper bound. It is very simple and kind of folklore. So we use a balanced separator, which we know it exists, and it's balanced because kind of half of the disk, roughly half the disks are inside, half of the disks are outside, and not so many disks are intersected. And the number of disks that are intersected depends on the ply, meaning how many disks, like how densely are those disks, right? And how densely those disks are depends on the number of colors. So if you allow a lot of colors, maybe these disks could be very dense. So yeah, then what we do is we look at the separator, we look at all possible colorings, and yes, and then we recurse in the inside and on the outside. So these balanced separators, they are known for all kind of fat objects. They don't need to have all the same size, so they could be homosets of one another. One could be larger, that could be smaller. But it was really needed that things are fat. And what is not fat, well, segments are really the one object which are not fat. So we were interested in what happens for segments. And it turns out that for segments, we don't get such a speed up. So we have corresponding lower bounds already for constant number of colors. Coloring a segment in the second graph cannot be faster than 2 to the lower bound. And I guess the reason kind of is that this color maybe is red here because it intersects this blue segment, but then far away it also can transport this information. I'm red, right? Although locally these two things have nothing in common. And so yeah, let's give this interesting lower bound. Okay, so for the remainder of the talks, I will give you the ingredients for our main contribution, which is this lower bound, and we use some insight which comes from this lower bound from independent set. Okay, so there's this reduction from click to independent set, and it looks a little bit like this. We have a click instant, and then we generate this grid of clusters of disks. So this you can look up in this Parameterized Algorithms book, which is one of the standards books, I guess, on parameterized algorithms. And here there's this platypus. I love the platypus, it's really cute. And so the idea is that the reduction, it turns out that you can take one disk on each of these clusters if and only if there was a and these disks will be independent, form an independent set of disks, meaning they don't intersect, if and only if there was a click in the previous in the graph that we used for. And I don't want to go into any details of this reduction, but I want to tell you a little bit on how these clusters interact. So because there's this one insight from this reduction, namely disks are octagons. So let's look at the disk centers. So the disk centers here, they're placed on a tiny grid. So all of them are placed on this grid somewhere, and here they're also all placed on this grid. And then it holds the following. So if for this red disk here, it will be on a column farther to the left than the blue disk here, which is here. So it's your second column, your third column, then these two disks will not intersect, as you would expect from octagons. And on the other hand, if the column of the red disk is farther to the right, so here it's a fifth column, then for the blue, which is here the fourth column, then they will intersect, as you would expect for octagons. In case that they're on the same column, they kind of really touch, that they don't intersect. And there's no way to cheat. So let's say you say, okay, maybe here the red one is further to the right than the blue one. So it's fifth column, it's fourth column. But maybe I can cheat because I'm super high and that blue column is super low. But this doesn't work because disks are octagons. At least if these grids are super small, because then only the tangent of the disk is important. Yeah, and so with this insight, I want to start. I hope this is clear. Yeah, otherwise look at those pictures again and here. You have to trust me on this. You can do these calculations. It's not so difficult, but I hope it's convincing from a picture. Okay, so how can we use this for coloring? So we can copy one coloring from one cluster to the other. So we have here this cluster of 5 disks, and let's say they're colored in a specific way, and we have exactly 5 colors, and those disks must be colored exactly the same way. Because why? So here's the first disk must be colored blue because it intersects all the other colors except the blue disk, so it must be colored blue. And then the next one, it's colored blue because the blue one is already in the same cluster, and then it intersects brown, yellow, orange, and so on and so forth. So we can copy colorings, right? And that motivates us to define a variable assignment in a way that we always have 2 points for one variable, and there are 2 ways to color them, either 1, 2 or 2, 1. And here also for x2, it's 3, 4, 4, 3. And one of those colorings we interpret as true, and the other we interpret as false. And this has a huge advantage, or kind of the immediate insight, that we can transport these colorings or these variable assignments in a way that we want. So yeah, and once you write it like this is, once you know that you can transport a variable assignment in the way that you want, you're done. Okay, so note that there is some grouping here. So we want to use roughly n to the alpha colors. Right, this is where we start from. So this is roughly the same number of points that we have per cell then. And this also roughly corresponds up to constant factors to the number of variables per cell. Okay, so this idea to let us transport variables and split variables or bunch of variable assignments. And once you have that, you have a strong indication that you're on the right path. Okay, so let me tell you how to do this grouping. Okay, it works as follows. You have n classes, and you group these classes into disjoint groups, each of them having size n to the alpha. Yes, and then what you do is, for each of those groups, you look at all the variables. So we reduce from 3 set. This means that also here all these variables have they are also roughly n to the alpha variables in each group. But while these classes were disjoint, and now these variables are not disjoint. They might be overlapping because a variable might appear in several classes. Okay, and then this is how we arrange all these variables from like a high-level perspective. So each variable group gets a row and a column. So here this first variable group gets the first row and the first column, and the second variable group gets a second row and second column. And then they will meet somewhere, and they, like v2 and v3, they will share clearly some variables, or they might, maybe not. But we just check at this intersection point for consistency that those variables which are shared are given the same assignment. And on the boundary here, we can check all the clauses. So that's the overall idea. So now I have to tell you a few things like that I want to come to, like how do we do clause checking, how we check consistency, and how exactly do we do this here? What's going to happen over here? Okay, so there's so I will tell you this in a second, but there are 2 ingredients that you need to know, or a few. One is that you can forget about assignments. That's super useful, right? So maybe here the first variable is assigned to true, the second variable is assigned to true as well, and we just want to forget about this assignment. We don't need it, right? Maybe we just, okay, we don't care about it. So what we do is, these 2 points here, they're both placed in the same column, so either can be colored 1 or 2. So we could have column 1, 2, or 2, 1, and both of them will work. And then this will be transported. Yeah, we can use this in a more sophisticated way, but I just wanted to show you here the principle, and I hope you trust me later that whenever we need to forget something, we can do it. We can also permute stuff. So yeah, so I first had all the points on a diagonal, but we don't have to do that. We can use like a permutation of the points, and then suddenly they all need to be in a different order. So maybe the color 3, 4, which was used in the 2 last columns, they now will be used in the first 2 columns. Because from here to here we copy column to column, and from here to here we copy row to row, but we can do any permutation that we want. Again, I will use this in a more sophisticated way, but when I will use it, I want just you to trust me that I can do it if needed. Yeah, and then there's kind of one thing that was or confusing us most, which was, okay, so we need to give meanings to these names, right? So I talked about having color 1 and 2, but there's no real meaning of 1 and 2, right? So these are just arbitrary names that are given, and somewhere else, maybe different colors might be given to names 1 and 2. And so in order to fix a meaning of each color, or a name that kind of can be consistently addressed to, what we do is we fix one cell somewhere where there's one cluster of this, where it will be colored in an arbitrary way, but whatever that coloring is, that will give us a name. So whatever this disk is colored, we will call this color color 1, and so on. So this will give us, for the future, the name of each color that we can use consistently. Yeah. Okay, and then together with that so-called reference coloring, we can use Clause-Gadget. I don't want to go here into details. You can check that this works, but essentially it's a clever application of forgetting and permuting. And yeah, that's what check, I don't know, clause x1 not x2 x3, something like this. Yes, and what I want to stress here is that you need the reference coloring, and also that you might want to check that two variables are the same, that you can do with these two clauses, right? x1 or not x2, and not x1 or x2. That makes life very easy for us. Yeah, so now we can assume that we can do that as well, and not just cross checking. And okay, so now before I can give you the final big picture, then that will make everything useful. Let me just say the following. So we have this reference coloring in one cell, and we have to bring it everywhere, right? Because like if we want to check clauses, if we want to check equality, then we need this reference coloring. Otherwise, things don't make sense. So, but then also our variable assignment goes everywhere, right? We want to transport our variable assignment as well. So I want to explain you here how we cross a reference coloring. So the reference coloring should go from here to there, and the variable assignment should go from here to there. And I want to explain you how to do that. So the trick is very simple, namely double the variable assignment. So we have here the variables and have them some assignment, and then we have them here again with the same assignment. That seems kind of overdoing it, but see what happens. So since we have them twice, we can just forget half of the variables, namely the lower assignment. We forget it, and instead we replace it by the lower part of this reference coloring, and how the lower part of the reference coloring gets through. But okay, so since we have our reference coloring and the identity gadget, we can restore that, so we can kind of forget this part and make sure that the variables assigned on the top and on the bottom are the same. So we can restore our variable assignment at the bottom again. And hey, here we are. We've got our full variable assignment twice again. And now we forget the upper part and do the same again. And at the end we have the full variable assignment. And so we transport here the upper part of the reference coloring, and then we put these two reference columns together, and then we have got the full reference column here. So this is very neat. It took us like 2 days to figure that out, and was like a major struggle for us, but it's very simple, and I hope I could convey this idea. Okay, so now we are ready to kind of finish this up. So okay, so I told you how we do this grouping, where each group gets a row and a column, and so we assign some variable cells which store all those variables according to the grid cell that we're in, and we can connect all of those with wires. Okay, there will come more, but in principle we can transport variables from here to there, those which are shared. We place a reference coloring everywhere. Okay, I will tell you later what we do then, but imagine we have a reference coloring everywhere. Then we can check for those variables which are here and there where are some in common, that the assignment is consistent, that they have the same assignment. We can do this with some consistent, well, with some identity gadget, and the reference coloring, which we have everywhere, right? And then what we need is we need to say, okay, so we have to connect this reference coloring to all the other reference colorings, and we will use these crossing gadgets, as I explained before, which we need as well. But we can do that because, well, we have the reference coloring available to also do the crossing. And yeah, at last we need to place clauses, so we only need to place them at the outside. And these clause gadgets also work well because we have the reference coloring everywhere. Okay, so this is a big picture. I hope that yeah, I could convince you that this works and bring across some of the main ideas. And yeah, thank you for your attention, and hope you enjoyed the talk.